The last algorithm we are going to discuss is the cheapest link algorithm. Now, the cheapest link algorithm has 5 steps. The first step is to pick the edge with the smallest weight. This is a different algorithm, so we don't care about the reference point or the starting vertex. All we're looking at is the picture, the model in a whole, and we're finding the smallest weight, and that is going to be the edge that we pick. Step 2 is to pick the edge with the next smallest weight, and then we keep doing that, except if it closes a circuit. And what I mean by that, I have this little picture right here. A, B, C, D. And I'm going to do a pretend example just to show what it means to close a circuit. So let's say in this pretend example that AC has the smallest weight. This is made up. The next edge that has the smallest weight is BC. The next edge that has the smallest weight after that is AB. But what happens is when we choose AB, we close the circuit and we're never able to get to vertex D, and we need to get there. So what that means is that even AB would be the next edge with the smallest weight. We are not going to pick that edge because it would close the circuit. So that would mean that the edge AB is not an option. So we continue picking the edges with the smallest weight, except if it closes a circuit, then that means that edge is not an option. We go on to the next one. Or if 3 edges come out of a vertex. So I'm going to move over here. Let's say we have an example, and AC is the smallest one, edge with the smallest weight. And then BC is the next smallest. Well, if CD was the next smallest, what that would do is that would cause us to have 1, 2, 3 edges out of a vertex, and we can't do that. So even though CD would be the next smallest, CD is not an option. So what I like to say is once we have 2 edges coming out of a vertice, I like to call that vertice closed, and I just put a star, and that just reminds me that no other edges can come out of C. So we keep picking the smallest edges unless it closes a circuit, or if there's 3 edges that come out of a vertex, we can't do that. Once a vertex has 2 edges coming out of it, it's closed. Okay, and then it goes to step 4. When only 2 vertices are left that aren't closed, then you know it's time to close a circuit. So I'm going to do a made-up example again just to illustrate what that means. So let's say this is the smallest edge, and then the next smallest edge is BD, and they don't have to connect. That is okay. Let's say the next smallest edge is BC. Well, what happens? Well, B, there's 2 edges coming out of it, so now B is closed, and there's also 2 edges coming out of C. C is closed. Now, if you see, every other vertice is closed except for the last remaining 2. A is open and D is open. And when there's 2 vertices left that are open, then you know it's time to close the circuit. And there you go. Now A is closed and D is closed. This would be our circuit. So that's what step 4 means. When only 2 vertices are left that aren't closed, it's time to close the circuit. And then step 5 just states that you write the circuit starting at its designated reference point. So whatever the reference point would be, like in this example, the reference point is going to be D. Well, we have our circuit under the, and so we would just write it using D, starting at D. D, B, C, A, D, or the mirror image D, A, C, B, D. So that's basically the cheapest link algorithm. Now let's actually use a problem with the model. Right here, this K4, complete graph with 4 vertices. And I like to create a pictorial over here on the side. And we're just going to be, The one thing that we need to know is that the reference point is going to be D. We're writing this for a salesperson that lives in Denver. So they need to go to 3 other cities, Atlanta, Boston, and Columbus, and then they need to go back to their home city in Denver. So we're just going to start, and we're going to pick the edge with the smallest weight. And if you look at all the numbers, 60 is the smallest number. So I'm going to choose the line segment AD. The next smallest number would be 70. Now it just so happens that they both they're touching Denver. They don't have to be. They could totally not be touching. They don't have to be connecting at all. It just so happened in this example that they are. So we have 60, 70, but look, Denver is now closed because there's 2 edges coming out of it. So let's go ahead and pick the next smallest number. The next smallest number would be 140 BC. Uh, 140, and B is closed. And now we are just left with 2 vertices that are open. So it's time to close the circuit, and that is 210. So we're just going to write it with our reference point. Our reference point is Denver, D. So it would be D, B, C, A, and D. Or the mirror image D, A, C, B, D. D, A, C, B, D. Let's go ahead and add up all of the edges. DA would be 60, DC would be 210, CB is 140, MBD is 70, and that's a total cost of 480. So that would be the answer of this particular problem using the cheapest link algorithm. We're going to do one more example just to practice this. The cheapest link algorithm. So what we have here is a K5. This has 4 vertices. I mean K5. K has 5 vertices. There's A, B, C, D, and E. Our reference point for this problem is going to be E. So at the end of this, we're going to start this at E. We're going to write it starting and ending at E. So what we're going to look is we're just going to find the number that is the smallest number in this model. And if you look, 119 is the smallest. The next smallest, and see how it has nothing, it's not touching E at all, and that's fine. We don't worry about writing it at E until the very end. The next number, looking at it, that is the smallest number, looks like 120, EC. And if you see, C is now closed. There's 2 edges coming out of C. The next smallest number is 121 from C to B, but what that would do, C is closed, so we can't use that option. That option is out. The next smallest number would be 133, but 133, that would close the circuit, so that is not an option either. So the next option, the next smallest number would be BD for 150. The next smallest number after that would be AD for 152. And what happens is there's 2 edges coming out of D and 2 edges coming out of A, so they are both closed. And finally, it is time. There's only two vertices that are left open. Everything else is closed. We now know it's time to close the circuit, and that would be EB. So the circuit this is the Hamilton circuit using the cheapest link algorithm. The next thing is just to write the circuit. So we're going to use our reference point of E and have E to B to D to A to C and then back to E, or the mirror image, E, C, A, D, B, E. E, C, A, D, B, E. And you could add up all the weights of all those edges for the total cost.